Okay guys, I think we can start today's session. So let me take the syllabus. So we have been discussing about the turtle sim stuff like the programming of turtle sim using RCL Pi and RCL CPP. We have been discussing in the last class. I didn't upload the video yet. Maybe together with this video I can upload. I think video is uploaded, but notes are not yet uploaded. So today, we are going to discuss the second part. Second chapter. The topic is TF. Okay. I hope you already aware of TF, the transformation library that we have already worked with the ROS1. And if you forget that, then I can share the library with you. 1 second. So this is the page. Just a second. I think I have taken that. 1 second. Let me close all this stuff. Okay. About TF2. Yeah, this page. Maybe I can share the link. This is what we are going to refer. Wait a second. Yeah. So the documentation that we are referring is with the Foxy. Okay. And but the concept is the same. I think we have seen the same image or the diagram in ROS1. So basically the TF library in ROS, or even in ROS1 or ROS2, is basically for keeping a track of the frames. For example, if you take a robot, okay, a robotic system, maybe you can check these this robot called PR2. Okay, so PR2 is having multiple joints. Okay, multiple joints. It is having wheel joint, then there is a head, then there are two arms. So each joint having different joint values, and so these joint values are converted into transform. Okay, and these transforms are keeping, or like it's generally publishing, subscribing, and generating everything doing by TF library. So TF library is doing all the stuff regarding the transformation in ROS. So why this library important? I think we already taken the session about TF in ROS1, but I'm just repeating because this is very important part of ROS1 or ROS2. So simply this library help you to listen to the TF or transformation from one joint to another. So why we need to listen to a transform? Maybe I can say an example. If we want to do a pick and place operation, maybe I can pick and place robot arm or something. Okay. Yeah, I hope you have seen this kind of application. Okay, picking and placing, simply picking and placing application. So the object is on the box. Okay, so maybe the pick and place, it can be sorting application, then some kind of classification. It can be anything. Okay, so the object is detecting using a camera mostly. Okay, a camera may be on the gripper or in some position, maybe a global camera or something. So that camera is helping the robot to see. Okay, and that camera will detect these objects. Okay, it will find the object and it will be returning with the centroid of the object. Okay, so what is the next step? After getting the coordinate of the object, the robot has to go to this object and pick the object and place it somewhere, right? So how can we do that? Because we are getting the coordinate with respect to the camera. Okay, but in order to reach the robot to the object, we need what? We need the position of the object with respect to the robotic end effector. Okay, so then only we can command the robot to go to a specific position. Okay, so somehow we have to transform the camera coordinate of the robot into the end effector coordinate or the gripper coordinate. Okay, so that's where the transformation is coming, because in order to find, okay, in order to find the robot coordinate, okay, if you know the transformation matrix, okay, or like maybe in simply like if you know the relationship between the camera pose and the end effector pose, okay, then you can compute the robot coordinate of the object if you get the coordinate from the camera. Okay, like if you get the camera coordinate, you can convert into robot coordinate using the transformation. Okay, so that is one of the main application of using the transformation, because we can compute the position of the robot with respect to another frame. Like if we have the transformation of the robot with respect to the world frame, then world frame means like a global kind of frame. We can compute the robot coordinates in another transform. I mean another with respect to another frame. So these are some of the use case, and this is very useful in robotics, especially if you are creating application. Yeah. So this TF2 library, transformation library, is the same. I mean the concept is same for ROS1 and ROS2, and in ROS2 the APIs have some changes. Okay, APIs having changes. So basically the TF that you are seeing, okay, this is a visualization of the TF. The TF we can publish it. Okay, publishing TF, we will say another word, broadcasting. Okay, we will be broadcasting the TF, or we will listen to the TF. Okay, listen means subscribing. Okay, so there are some APIs from the TF2 library which will help you to publish these transformation. Okay, and we can also listen to it. Okay, so commonly in ROS, the TF, the transformation is having a tree structure. Okay, tree structure in the sense, maybe I can show you TF image or something from the, okay, yeah, so it's like this. So there will be a global coordinate, or like base link or world. With respect to that, there will be branches. Okay, so this is the structure, meaning there will be a base frame. For example, if you take this robot, there will be a base frame, that is the initial, or the with respect to the base frame we are defining all these frame. So there is a convention in ROS, so we will be mostly keeping the base frame as the first frame, okay, of the robot, okay, and then with respect to the base frame we will be defining other links. And there is another convention, like there is an imaginary frame, okay, frame or coordinate system, you can say like a coordinate system. With respect to that we are defining all these things, okay. So like if this is base frame, then with respect to the base frame the wheel are like XYZ rod PTO, okay, with respect to base frame. So there is another convention, like we will be using base footprint, which is an imaginary axis just below the base frame. So these are some conventions that we are using. Anyway, like I just mentioned about the TF2 library, what is its advantage? Mainly to keep the transform. We can broadcast the TF. Basically broadcasting means we can publish the TF between transformation between two frames, or we can listen to it, okay. So in order to program this we can use C++ or Python mainly, okay. And so this section of the tutorial, like if you just go to ROS2 tutorial humble, you can find a section on the left side. It's in the intermediate side, okay, intermediate heading. You can find TF2. So that is what I am talking about, okay. So here in the tutorial we are mainly discussing about, like there is an introduction, and then they are talking about the broadcasting. Broadcasting means sending the TF, then listening to the TF, and we can create a frame, new frame. Frame means like with respect to the base link, if you want to create a new frame, maybe a new wheel or new joint if you want to add, then you can add a frame, okay. And then we can like traverse back, like if we have the buffer of this TF, buffer means the a storage, or like if we have the list of TF, TF mainly having the timestamps, so we can traverse back and forth, okay. So that is what it's mainly saying. So in the introduction or like in the main documentation, ROS2 documentation, they are talking about the basic stuff, all the basic stuff that we require. And for broadcasting they are also discussing the Python part and C++ part, okay. And it's almost similar to ROS1. So if you remember the stuff, maybe we can start with a demo that we have worked with the ROS1, so you will get an idea, okay. So this is an excellent example to show the main application of TF, okay. So let's start with the example so you will get an idea, okay. So we already demonstrated in ROS1, okay. So in order to start with this, there are some dependency packages that we have to install, okay. So the demo is based on TurtleSim, okay. So just copy paste this command. Basically it is installing, it's checking whether we have RVis2. Then there is a new package called Turtle TF2Py, okay. Basically this is a package which is having this demo application. And then there is TF tools, okay, TF tools, and then TF tools I will explain that, and it's also checking the TurtleSim is installed or not, okay. Okay, so let's start with the the demo. So if you have Ubuntu laptop with you, maybe you can also try. Okay, just a second. So let me take the Ubuntu my side, and I'm just maybe I can open the tutorial from here. ROS2 Humble TF2, and here it is. Okay, so this is the first command. Basically, the command is launching a launch file, and the launch file is having the application. Okay, so we can see what is happening when you start launching this. Okay, after showing the application, I will be discussing what's going on. Okay, so here you can see two turtles. The green turtle here is basically tracking or following the blue turtle. That's what we have seen, right? We have started the application, and immediately after starting, the green turtle reached near to the blue turtle, right? And now what we are going to do is we are teleoperating the blue turtle. Okay, so I'm just copy pasting the command. It's basically the turtle sim teleop. I think you are familiar with this command. So the turtle sim is here and the teleop is here, and then I'm just trying to move, and what happening is that the green turtle is somehow is following the blue turtle. Okay, but you can observe it's not following the path. Okay, the path that the blue turtle taking, it's not like just mimicking the path, but it's trying to find the shortest path between these two and then reaching it. And it's not doing that at one time, it's continuously doing that. Okay, we can't we can't escape from this. I mean, the blue turtle can't escape from, because it's continuously monitoring the blue. Okay, but it's not following the path. So how is this application how can we create an application like this? Okay, so that's what we are going to see, and the application is using TF. Basically, we can see how the application works. Okay, so I mentioned that this application using TF. Okay, and in order to inspect what is going on in the background, we can basically use the ROS tools, ROS commands, right? So like I can simply check the topics, ROS2 topic list. So as you know, like there are two turtles. So for two turtle, you can see the command velocity, then the pose topic, which will give the pose of the robot or the turtle. So these are the things, and we can also see a new topic, which is TF. Okay, so basically if you are publishing or like broadcasting a TF, the TF is actually publishing in a topic called TF itself. Okay, you can publish multiple transform. Basically, a robot will have multiple joints and multiple frames basically. So the TF is a kind of global topic, okay, which is having the transformation of all the frames. Okay, so once we listen to this topic, we will get the transform between all the joints, all the frames, and then we can listen to the specific combination. For example, I mentioned that the TF is like a tree structure. So if you want to listen to specifically like world frame to turtle1, you can simply listen to that itself. Okay, or if you want to listen to world frame to turtle2, you can listen to that. So listening you can decide, and also you can broadcast based on your application. Okay, so what we can do is you can simply echo the TF topic called TF. So what is happening in the TF topic? So I'm just simply echoing it, and then what you can see is there are two transform it's basically publishing. Okay, before that I just want to show you what is inside the TF topic. I mean, what is the message, ROS message that we are using. Okay, so in order to do that, ROS topic info TF. So you have seen the TF topic is using a message called TF message. So you can simply copy paste it, and then if you simply search it, you will get the message definition. This is actually from the ROS1 documentation, but basically this is from the ROS2 documentation. Basically the TF is having an array of message, and the array of the message basically from the geometry message transform stamped. So that means it is having an array of transformed stamped messages. So what is the transform stamp having? So the transform stamped and individual transform stamped message is having a header, then there is a child frame, and there is a transform. Okay, and what is the transform having? The transform having translation and rotation. So basically the TF topic is having individual transform. Okay, you can see the child frame, right? Child frame means you can say world is the parent frame and turtle1 is the child frame. Okay, so child frame in with respect to, if you are saying a transformation with respect to a frame, then that frame is called the child frame. So for example, if you take if you check this image, world is the base frame, or like the root of this tree, right? So we can say world is the parent frame and turtle2 is a child frame. Okay, and world is a parent frame, turtle1 is the child. Okay, so if you simply check the topic echo, if you are echoing it, you can find the message like this. Like inside the transform, this is a header portion. Okay, header will have the timestamp and the base frame, okay, or the root frame with respect to this child frame is publishing. Okay, so the turtle1 is with respect to the world frame. Okay, and this is the transform value. Okay, translation and rotation. And if you just scroll down, you can see the transform of turtle2 as well. So in this message, if you simply echo it, what basically happening is that you can see the turtle1 and turtle2 transform is continuously publishing. Okay, and do you want to visualize the TF? You can visualize the TF in RViz, right? Okay, there is an option in visualizing. So what you can do is you can simply set the fixed frame as world. Fixed frame means, here I think you got an idea. Fixed frame means with respect to this fixed frame, the TF or the transform is showing. Okay, so you can select you want to visualize the TF with respect to world frame, turtle1 or turtle2. Okay, so if I'm setting world frame, then you can see with respect to the world frame where is turtle1 and turtle2. Okay, so by the way, the turtle1 and turtle2 is the transform of the two turtles that we have seen in the simulator. Okay, 1 second, let me just increase the marker scale and all. Okay, yeah, so to view it better. Okay, so currently you can see the turtle1 and turtle2 are in the same pose. I will not say pose, but the position, the translation value is correct, but the rotation yeah, I mean it's almost correct. That's it. Okay, it's trying to match with the translation and rotation, I guess. So you can see the TF, you can watch closely. 1 second. Okay, here is the simulator, here is the visualizer of TF, and let's see the magic. 1 second. Yeah, if I'm teleoperating it, the turtle1 frame is moving. You can see it, right? Okay, so basically the application that we are talking about, okay, that we have started already, it is broadcasting the transform of turtle1. Okay, so whenever we move the turtle1, the application that we are running is publishing the transformation. Okay, so so where is the world frame? You can find the world frame. Actually, the world frame, let me see, I think it's on the bottom side. Okay, so this is the reference points. You can see the turtle1, this is the, so with respect to this pose, okay, so this is 0 0 basically on the left here. Okay, so this is taking as world, and with respect to that, if you move the turtle, you can see in the x-axis it's moving, and if we move up, it is moving around. Okay, so you get an understanding, right? The application that we are talking about is broadcasting the pose or the TF. So how can the application broadcast the TF of turtle1? Because the turtle sim that you are seeing is publishing the coordinates of the turtle1. You have seen this topic, right? If you check the topic called turtle1 pose, okay, so from this you will get the pose of the robot. Okay, x, y and theta. Theta means rotation, so in order to publish the transformation, basically ROS using quaternion, not the theta value. I mean, it's actually using the quaternion value, so we have to convert the theta into quaternion. Okay, so we can see that in the code. Okay, this is in the Euler domain. We have to convert into the quaternion. So like ROS is actually using that. Okay, so that conversion is there. So basically from this pose we are publishing the TF of the turtle1. Okay, and what is turtle2 doing? Any idea? I mean, what is turtle2 doing? Like, it's simply following the turtle1, right? And how can it follow? I mean, it's not simply copying the path. So it's not keep on track with the pose. I mean, not the path, but it's keep on tracking with the pose. So it's actually very easy. So if you start a turtle in the turtle sim, it will also give you the pose of the turtle, right? For example, if you check the ROS2 topic list, you will get the pose of turtle 1 and turtle 2, right? So what happening is that this application will be publishing the application that we are talking about. Okay, the application, this one, the demo.launch.py. Okay, so this launches the application. Okay, so we will be seeing that. So that application will be publishing the TF of both of this turtle. Okay, both of the turtle. Okay, and inside that application, it will be taking the difference, or it will be listening to the transformation between turtle 2 and turtle 1. Okay, because this is a tree structure, right? So like using the TF library, I already mentioned that we can able to get the transform between two joints or two frames. So here the turtle 2 and turtle 1 are two frames and it's connected in the tree. Then only it is possible. Okay, so if it is from the same tree, then we can find the transform between these two. So what is the transform? Transform basically having the translation and rotation. Basically, how much distance from turtle 2 to turtle 1 or turtle 1 to turtle 2. So basically it's giving the error between turtle 2 and turtle 1 pose. Okay, so once you get the difference between the pose, the application is written in a way that it will be generating the command velocity in order to minimize this error. Okay, so the robot turtle 2 is the follower. So whenever the turtle 1 moves, the error between turtle 2 and turtle 1 increases, and then based on that transformation, it's creating the command velocity. So the command velocity will be produced and the turtle 2 will start moving, and the error will be the objective is reducing the error. So the robot will be start moving and following along with the turtle 1. Okay, so this is an interesting example to demonstrate how the TF works. Okay, so we can see we can play around with this application in order to get an idea. So you have seen this one, right? So I mentioned that we are taking the transform between two frames, right? Turtle 2 and turtle 1. So there is an option to visualize the current TF, and also we can echo the transform between two frames, because I mentioned we are taking the transformation between turtle 2 and turtle 1, right? So if you want to echo the transformation in order to debug or something, if you want to echo the transformation, you can do that. Okay, so this is an example. I can explain the command after this. One second. So the command is ROS run tf2 ROS tf2 echo. Tf2 echo is the node name, and you can see the transformation metrics. So I can explain the command first. So the command is ROS2 run means running a node, okay, from a package called tf2_ROS, okay, and the node name is tf2_echo, okay, and we have to pass two command line arguments for this node, okay. One is the source and target, I guess, okay. So that is here, source and target, okay. So source we have set as turtle2 and target as turtle1, okay, because turtle1 is getting targeted, right? So if you do that, currently you can see the situation. Maybe I can simply move the turtle to some pose. Okay. Okay. Yeah. So now I'm just echoing the transformation. So you can see what is the value of translation. What is the value of translation? It's 0, right? And there are some value in the rotation. Okay. So what is this means? What is the meaning of this? If it is 0, then it's in the same pose, right? Maybe I can show you the same values when we move the turtle, okay. So I'm just moving the turtle after this. 1 second. Okay, so I'm just moving it, okay. So now you can check the translation value, right? Okay, you can see the translation value is getting changed, okay. Why it is changed? Because we are continuously taking the transform between these two turtle, okay, and there is a translation error happening, okay. So once I'm stopping the robot, imagine if I'm just stopping the robot here, you can see the translation value is approaching to 0 after some time, okay, because the error between these two is getting reduced and then it's getting 0, okay. So this is a simple application that we can I think there are a lot of interesting projects in the first batch in RDLP 1.0. Students actually use these simple approach to create a snake game in Turtle Sim. uh, and this transform is the main key thing that they have used, okay. So you have seen this tf2 rows, okay, tf2 rows. This is an inbuilt package in ROS1 and ROS2, okay. So which is having a set of nodes which can be used to debug the ROS tf structure, okay, tf3. So debug means like if you want to echo the transformation between two frames, you can do that, okay. And if you want to like visualize the tf3, you can do that. So there is a command called view frames. It's not a command, it's a node called view frames. So I can show you that. Just switching to desktop, and if you execute this, it actually showing some messages, right? Okay, and I'm just checking the desktop, and you can see where is the desktop? Yeah, you can see two files. One is PDF and one is .gv. So you will get this PDF that is mentioned in the documentation. Okay, so this tool called view frames. Okay, inside the TF2 tools package there is a node called view frames. This tool basically listen to the TF. Okay, listen to the TF, and it will be checking for the TF tree. Basically, if you listen to the entire TF, you will get what are the frames that is publishing, what is the base frame, all these things. So after listening to that, it will be drawing this TF tree into a PDF. This is very useful while playing with a big application. So like you will be publishing different transform, and then mostly you don't know like what happening to the transform after some time. So you can able to visualize it using this, and you can also echo it. Okay, so these are the main thing that we can do with this TF2 tools. Okay, it's very useful. Okay, one second. Yeah, so this was the first example. Okay, you can also try on your computer just to see how the TF works. Okay, and after that we can jump into the next tutorial. Like you can simply go to the next one, which is the static broadcaster. So if you simply go through it, obviously I don't think it will be easier for you to understand, but I will say like you have to understand the concept first, then go through this. Okay, then only it will be easy to understand this. Because if someone having the knowledge about this, if he explained before reading this stuff, then I think it will be useful to you, because you will have an idea what is this page about. Okay, so I would like to give you a short idea like what is this page about, and what is a static broadcaster, all this stuff. Okay, so like I mentioned, right, like the TF is like a tree structure, and the TF, mostly the TF is dynamic because the robot is moving. Mostly the robot is moving, the frames are changing. You can see the turtle 1 and turtle 2 frames, right? It's keep on changing, right? What about some frames that is not changing? Okay, for example, what consider a robotic arm. Okay, a robotic arm, and some of the frames or some of the joints are static. Okay, static means it will not move. Okay, it's a fixed joint. You know what is a fixed joint, right? But it's still a joint. Okay, it's still a joint in the URDF, but it's fixed. Okay, so in that case the TF is not changing. Okay, because the transform, the translation and rotation is the same. It will be constant even if the robot moves. Okay, so in that situation, okay, in some situation, if the transformation is static, then you can use the static broadcaster. Okay, static broadcaster. So there are normal TF broadcaster and there is static broadcaster. So static broadcaster can be specifically used for this kind of purpose. Like you can keep on publishing a TF, okay, and that will be useful in some situation. For example, I can say another example. Imagine a robotic arm, okay, and on the top of the robotic arm there is a camera, okay. So we are taking the reference with respect to the robotic arm base, okay. Maybe I can show you an image for better understanding. Not this. Okay, maybe, yeah, maybe this example works. Yeah, so some parts are not there, but my idea is that there is a robotic arm and there is a global camera, just maybe the side, it may be putting in the side or the top of the robot. So the position of the camera with respect to the robotic arm base is not changing because it's fixed, right? So in that situation, we can publish a static transform because it's not changing. We can publish it. We already know the transformation between the frame of the base of the robot and also the camera. Okay. So what is the advantage of that? The advantage is that if we want to find the object position with respect to the end effector, robot end effector, you can able to do that, okay, because you have to include the camera frame with respect to the robot frame, right? Then only you can access the transformation. So even if you are putting any sensor that is useful, maybe it's a camera or any sensor, you have to add that in the TF tree. Otherwise, the camera can find the object, it can retrieve with the object a centroid, okay. But how can we move the robotic arm towards the object if we don't know the position? If we want to compute the object position, then you have to find the transformation between the camera pose and the object, okay. There is a transformation between obviously camera will get the object coordinate, and then after that we have to transform the camera coordinates into end effector, okay. So basically we are multiplying the transformation to the end effector pose, and you will get the pose of the object with respect to the gripper or with respect to the end effector. So the static TF is mainly using for that kind of application. And if you check the topics, okay, simply if you check the topics with a TF based application, you can see 2 TF topics, okay. I'm not sure you have seen it. Maybe I can restart it. You can see 2 topics. So one is TF and another is TF static, okay. So the TF static basically having the static publisher, okay, static TF publisher, okay. But currently in our TF tree there is no static TF, okay. Only the normal TF is available. So you can see that in the TF topic. Okay, so that is what the static TF, which is very useful while we have to represent a sensor, or I mean some other I mean some other components of robot which is not moving. Okay, so we don't need to publish that again and again. We just need to publish it once. Okay, because we can save the bandwidth, by the way, because the normal TF will consume some bandwidth because it's continuously publishing. But the static TF, we don't need to publish it again and again, because once it publish, you are done. Okay, so that's why ROS is having these two things, like static and dynamic. Okay, so they are explaining about a code and all. Maybe we don't need to discuss that now, but maybe let me see in an easier way how we can do that. Okay, yeah, so I just want to add one more point. So I talked about the package called TF2-ROS, right? TF2-ROS. So which is having another node called static transform publisher. Okay, so what is it doing? It's basically publish the static transform, because the transform basically that we are publishing is not, I mean, having any change, right? So you can use this simply this command in order to publish a static transform. Okay, so maybe I think if there is an example, I can try that. So because it's a very big command. So basically, like using this, you can simply create any number of transform which is not having any change. So it's saying like frame ID, child frame ID. Okay, so I'm just giving maybe I can generate a static transform. Okay, so first they want to mention the frame ID, so I'm just setting the existing frame ID, which is world. Okay, we are publishing with respect to the world, and I'm just creating a new child frame ID, which is lengthen. Okay, there is nothing happening, and also I have to mention the XY, all the values. So I'm just putting 0, then Y as 1 and Z as 2, and all these things are 0, 0, again 0, and QW maybe 1. Okay, yeah, so it's publishing. Okay, and I just want to check, maybe better to check through, I mean you can use the view frame or RVs. Okay, we can use the RVs, and you can see the lengthen frame is already there, and I'm just visualizing the TF. So you can see here marker scale. Yes, so I have the lengthen frame here. Okay, and I have the turtle 1 and turtle 2 here. Okay, and if I'm moving the robot, I mean teleoperating, you can see the lengthen frame is not changing. Okay, that is with respect to the world frame. Okay, and I can show you another thing, another interesting stuff. So here we have put the world frame, right? What about putting the frame to turtle1. Okay, so what is the meaning of this? We are publishing a static frame or static TF with respect to the turtle1. So if turtle1 moves, the lengthen frame also moves, but the transform between turtle1 and lengthen will be the same. Okay, so that is the meaning. So here you can see the transform is there. And now let me move the robot. Okay, you can see turtle1 is carrying the lengthen frame. Okay, it's static only. I mean, static means that turtle1 to lengthen is static. Okay, so this is about the static frames or static TF. So we can see the programming part maybe next session. Okay, I think for today I think we can conclude this much is enough. Maybe next session we can see the programming part, like the broadcaster and listener. In static frame, I mean static transform, also there is some API that we can able to see. I mean it's the same in ROS1. In ROS1 also there is static frame. Yes, that's it. So I think we can conclude for today. Let me know if you have any question, guys.
What is the exact idea of this average rate, buffer length, most recent transform? Any programming significance?
Where
in that TF tree.
Okay.
On
Okay.
that
Here.
mapping.
Okay, here, right?
Yeah. Yes,
Okay.
yes.
Okay. So so the TF is publishing in a particular frequency, right? Frequency means the number of topics. Maybe I can just check that. Like you can inspect that rate of publishing using the ROS2 topic. So like ROS topic. So the TF topic is publishing, right? So in order to get the topic bandwidth, or like its average rate is like 125. Okay, 1 second. We can check the bandwidth as well. Yeah, so I'm not sure about the average. It's saying the average, but from the command that we are getting, like the average rate is like, its publishing rate is like 125. So 125 messages per second. That's what the thing. But from here it is saying like 62 that I need to check. But the buffer lengths mainly, I think, in order to visualize the TF tree, they may be buffered or they may be listened to this much of length. Meaning, in order to find this the TF frames, we have to listen for a certain length or certain time of TF, right? So when you do the view frame command, it will be waiting for a certain second. So mostly this is indicating that length. So they have taken this much of length to analyze the TF. So that is my understanding, Hari. So the average rate, I have confusion because the from the topic perspective, the average rate is 125. But maybe we can do that again. Maybe just a second. You can see it is listening for 5 seconds. So that is the buffer length, and it's saying rate is again 62. So mostly like it's a half of what we have seen. That maybe yeah, actually, like, yeah, it's a doubled. Maybe it's saying the rate of single transform. That may be my understanding, because the current TF topic is having two transform. The transform is with the world to turtle 1 and world to turtle 2. Okay, so there are two transform is publishing. So the transform of an average, if you are taking individual transform, then the average rate is 62, because what we are getting is 125, right? So obviously 125 divided by 2, it's 62.5. So I think that may be the reason. So average rate of one transform is 62. Is that making sense, Hari?
Yes.
Yeah.
Also, this most recent transform.
Yeah, that is
oldest
a
transform.
timestamp. So if you
Timestamp.
yeah, timestamp. So if you echo the TF, you can able to see the timestamp, right? So that is the timestamp. If you just check this, yeah, the timestamp is the thing. Yeah. Yes. So that is the decoding that, yeah. And they also mentioned the recorded at time this. Yeah. So I think that answered your question. And then any other question in the TF? So if you have an idea about the ROS1, then it's almost the same. The concepts are all almost the same. The APIs are different. I mean, there are some minor differences. Yeah, that's it. Okay. Okay, guys, I think we can conclude for today. Okay, next session I will be announcing, because like last week we have the Christmas and this week we have the New Year coming. So yeah, so let me see. We can set tomorrow, or maybe I can shift to some other day. Okay, so thanks for attending, guys. I will be uploading the notes and video soon. Okay. Good night, everyone. See you in next class. Bye.